All right, so today we're going to tackle a really cool concept. We're going to go from a simple single switch all the way to the very first spark of computer memory. Let's get into it.
So let's start with the central puzzle, right? How can a simple switch, something that's just on or off, be made to remember anything? I mean, think about it. A switch is totally forgetful. It only knows its state right now. It has zero memory of the past. So how in the world do we build a circuit that can actually hold on to information even after the original signal is long gone?
Okay, so to build something as wild and complex as memory, we've got to go back to basics. We need to find that one single fundamental building block, like our universal digital Lego piece that we can use to construct everything else.
And this is where it all begins. I mean, everything in the digital world. The bit. It's not really a physical thing. It's more like a choice, right? It's a choice between two states, on or off, true or false, a 1 or a 0. This is the absolute rock-bottom language our machines speak.
Okay, so if bits are kind of like the letters of this digital language, then you can think of logic gates as the verbs. They're the actual physical devices that take these bits as inputs, they do something with them, and then they spit out a new bit as an output. They're what bring the abstract idea of ones and zeros to life. Now, here's where it gets really interesting. You might think you'd need dozens of different types of these gates to build a whole computer, but no! In this amazing stroke of elegance, it turns out we only need one. Just one single universal gate that we can use to build all other logic. It's wild.
And here it is, the NAND gate. It's short for not and just take a look at its truth table. The output is always a 1, always true, unless both input A and input B are 1. And that's it. This unbelievably simple function is our universal digital Lego piece. This is what we're going to build everything with.
Okay, so we've got our universal Lego piece, the NAND gate. Awesome. But, a pile of Legos is pretty useless without some kind of instruction manual, right? Well, for digital logic, that manual has a name, Boolean algebra.
Yeah, this system, named after the man himself, George Boole, is basically the formal language of logic. It gives us all the rules for operations like not, and or. It lets us describe with mathematical precision exactly what we want our circuits of NAND gates to do.
And this timeline, it just perfectly illustrates the incredible journey from an abstract idea to world-changing tech. For almost 100 years, Boolean algebra was just this mathematical curiosity, a cool idea, but that's it. And then, this guy Claude Shannon comes along and has this light bulb moment. He realizes this 19th century math is the perfect language for describing electronic switches. And boom, the foundation for all modern computing is laid.
All right, now for the fun part. Let's see how this all snaps together. We've got our universal building block, the NAND gate, and we've got our instruction manual, Boolean algebra. Now we can actually assemble a complete toolkit of logical functions.
So check this out. It's kind of like magic. Just by connecting our NAND gates in these really clever arrangements, we can make them act like totally different gates. You take a NAND gate, you tie its inputs together, and suddenly it's a NOT gate. You take a NAND gate, you follow it with one of those NOT gates we just made, and now you've got an AND gate. And it just keeps going like that. And just like that, using only our NAND gate, we've built a full set of tools. We've got NOT, AND, or you name it. We can now perform any logical task we can possibly describe with Boolean algebra. So we're ready to build circuits that can calculate. But what about remembering? That's a whole different ballgame. So far, every single circuit we've talked about can only do one thing: calculate an answer based on what's happening right now. It's a calculator, not a computer. To actually remember anything, our circuits need a completely new trick up their sleeve. And this right here, this is the crucial distinction. The circuits we've built so far, they use what's called combinational logic. The key thing is, they're forgetful. To create memory, we need sequential logic. These are circuits where the output depends not just on what's happening now, but also on what happened in the past. This stored information, that's what we call its state.
So this is it. This is the million-dollar question that unlocks the next level of computing. How do we make that jump? How do we give a circuit a sense of the past? How do we make it hold on to a state?
Well, the answer is surprisingly elegant. And honestly, it comes from doing something that seems totally counterintuitive when you first hear it. What happens if we feed a gate's output back into its own input? We create a feedback loop.
See, instead of information just flowing in a straight line, from input to output, we grab that output and we route it right back to the beginning. And it's inside this simple little loop that the magic of memory is born.
So, by connecting two of our trusty NAND gates together in this special feedback loop, we create a brand new kind of circuit. It's called a latch. The key word here is bistable, which is just a fancy way of saying it has two stable states. It can hold its value, either a 0 or a 1, and just stay that way. Now, look at this table. Zero in on that hold state. That's the key to everything. We can set the latch to store a 1, or we can reset it to store a 0. But when both inputs are in that hold position, the feedback loop just takes over. The output gets, well, latched into place, and it holds its value. It is, for the first time, remembering. And that right there, that is the breakthrough. This is the birth of memory, a single bit held perfectly stable by a simple loop of logic. From this one tiny elementary memory cell, this latch, all of computer memory, from the fastest registers inside a CPU to the gigabytes of RAM in your phone, it's all built from this idea.
And this fundamental principle, it just scales up from one single bit to the billions, and I mean billions of bits in the devices you use every single day. Every time you save a document or load a game, you are relying on trillions of these tiny logic loops, all holding their state, all preserving the way a bit was set at some point in time. So if memory is really just logic gates in a loop, it really makes you wonder, right? What else can we build by just folding computation back onto itself? And that's really the big takeaway here. The simple, almost weird idea of creating a feedback loop is what transforms a forgetful calculator into a circuit that actually has a memory. It just goes to show you, immense, incredible complexity can come from the simplest of ideas, just applied in an elegant new way.